design a stack that supports push, pop. So we have a class. It's a constructor, push, pop, top, and the stack is a last in. Yeah, last in, first out. So you put a plate on top of the stack. Put a plate on top of the stack of plates, and the last plate you put on top is the first one you take out. So it's last in, first out. You have pop, which gets the top plate off the stack, and top, which just checks the top element. We have getMin. Design a stack that supports push, pop, top, and retrieving the minimum element in constant time. Implement the min stack class. Min stack initializes the stack object. Void push pushes the element val onto the stack. Removes the element on top of the stack. The top gets a top element of the stack. getMin retrieves the minimum element in the stack. To create the stack, we push -2, push 0, get minimum, which would be 0. We pop, get minimum, so push getMin, which would be negative. Yeah, we're pushing 3 onto the stack. Okay, -2, 0, -3. And we get the minimum, which would be -3. In constant time, we pop element off the stack and we get nothing. Push, getMin returns -3, pop. Should return an element. Oh wait, oh, pop just removes an element from the top of the stack. It doesn't actually return the removed element, only top does. So top returns 0 and then getMin, which would be -2. Interesting. So how would you design it so that you get constant time? So push, pop, and top, you get constant time for free if we just use this dot stack is an array, and if we push an element onto, we push val onto the stack, it would be this dot stack push val, and if we want to remove an element, we'll just do this dot stack dot pop, but only if this dot stack dot length equal 0. So if the stack isn't empty, then we'll pop it off the top. We'll pop the end of the array, which is technically the end of the stack. If we want to do top, we'll check if the array isn't empty, and we'll return this dot stack. So if this dot stack dot length -1, so just get the element at the end of the array. By getMin in constant time, how to do that? One way to do that would be, since we're adding elements to the stack from the top, we can't remove any elements in the middle, which means that the elements under the top of the stack, if we imagine it as a stack of plates, the plate directly under the top plate and the plates below it are frozen. So you can't take a plate out from the middle, otherwise all the plates would fall. That being the case, this means that we can keep a substack, maybe called min, and what we'll do is every time we add an element to the end of the stack, we'll set the new minimum for that element in the stack. So if we have potential elements added to the stack are, like I said, -2, 0, and 3. These are just the elements that we're going to add. Stack is going to be equal to nothing. Min stack is going to be equal to nothing. So when we add it to the stack, we'll do the math. We'll push the minimum element, the smallest element so far, which is actually going to be the element on the top of the stack right, at the top of the min stack, which is empty, or the element that we're pushing onto the stack. Right, so if we're pushing on -2 into the stack, right, then the smallest element we've seen so far is -2. Push 0 onto the stack, well, in that case, the smallest element we've seen so far is still -2. Now if we push -3 onto the stack, the smallest element will be the math.min of -2 or -3. So that's what we return. So we'll push this onto the stack, and then we'll do min_stack.push. Actually, and this will only be if this.stack.length 0 does not equal 0. There has to be at least one element in the stack. Otherwise, right, we just want to do min.stack.push val. Since the stack is empty, the smallest element we've seen so far is just going to be the element that we're adding to the top of the stack. Otherwise, we're going to do the math.min of min_stack, so min_stack.length -1, or the value that we're adding to the stack. So min_stack.push, the math.min of min_stack, so the last element in min_stack. It's actually min_stack.length has at least one element. Length -1, or val, and then we push that. So if we remove these, I think this should be good. And then whenever we pop an element off the top of the stack, right, if this min_stack.length not equals 0, actually these stacks are going to be parallel, so we only have to check for one. This stack.length does not equal 0, then we'll do this stack.pop, and min_stack also gets pop. And then for getMin, we can just do, it doesn't say what to get if the stack is empty. So we'll just return 0, I guess. So if stack.length does not equal 0, then we'll just return. I guess we can compress this. Does not equal 0, then we'll return this min_stack. So this min_stack.length -1, or we'll return 0. So if the stack isn't empty, then we'll get the last element in the min stack. Otherwise, if it is empty, then we'll return 0. So if we run this in our heads with the input of any other examples, -0, -2, they're going to push -2 onto the stack. So we'll just do s equal and min s for the min stack. We push -2 onto the stack. What's our push function? Pushes -2 onto the stack. If the min stack is not empty, well, it is empty, so we'll just do the same thing for min stack. The smallest elements we've seen so far is -2. Right, then they push 0. So go back to push 0 onto the stack. If min stack.length is not equal 0, well, it's not 0. Well, it's not empty, right? So then we'll push onto min stack the min of the last element, which in min stack, which is -1, or val, which is 0. So which is smaller, -2 or 0? It'll be -2. So for this element, the smallest element so far is -2. We can push -3. Well, we always just push the element onto the stack. Min stack isn't empty. So now we're going to push onto min stack the smallest of the last element min stack, -2, or -3. Well, -3 is the smallest. Then we do pop. We pop the stack. We pop the element on top of the stack. And we pop the min stack. So we get boom and boom. And then, oh no, we get min first. So if we get min, it would be -3, because at -3 be the last element in the stack, and the stack isn't empty. Then we would pop. We would get top, right? We would return 0. Then getMin, we would return -2. So this should be good if we run. This dot stack. Oh, oops. Oh, I forgot. I thought, oof. Stack on almost all of these. Okay, there's no stacks that are suffering from the same problem. This one is accepted, but I'm not even. This was done almost a year ago. It's pretty good. Right, only needs to return the value of the minimum. It does not remove items from the min stack. We're told that all the min stack operations must run in constant time. All of these technically run in constant time. Getting the last element in an array is always constant. Moving an element from the end of the array is constant. Pushing an element onto the end of an array is constant. So you get these 3 for free, and then getMin is what you have to do some specialty for. Alright, so BST, where heaps are not fast enough, we log event time, we want constant time. Right, it looks like we were fine to assume you should return -1, return 0, and there wasn't any elements in the stack yet. Have a go at writing a max stack class. So the max stack class would be the same, except we take the mat.max and we'd rename min stack to max stack. Invariant. So this is one way to do it. Invariant is something that is always true or is consistent. Recall that with a stack, we only ever add push and remove pop numbers from the top. Therefore, the important invariant of the stack is that when a new number, which we'll call x, is placed on the stack, the numbers below it will not change. That's kind of what we were saying with the plates. Numbers could come and go above, which could come and go above x for the duration of x is present, but never below. So whenever number is on the top of the stack, the minimum will always be the same, as it's simply the minimum out of x and all the numbers below it. So I think what they're getting at here is that, so it seems like I used two parallel arrays for stack and min stack, and you could accomplish the same with an array of tuples, where each tuple, the first element would represent the actual min, or the actual element at that stack, and the second element in the tuple would represent the minimum at the time of adding that element to the stack. even when we put a new number on the underlying stack, we need to decide whether the minimum at that point is the new number itself, whether it's the minimum before. It makes sense that it would always be the smallest of these two values. This also simplifies pop, since I guess you could just remove the tuple and it does both for you. So they're using an actual stack for the implementation of this problem. And then using these tuple is useful if you use the stack implementation, the built-in stack implementation. 2 stacks. This is what we did. Makes sense. So function is symmetric. Root, colon, tree node, or null. So we have a function which is a root or a tree node. Tree node has val left and right, and constructor for val left and right, and returns a boolean. So we have a binary tree node, and we're returning true or false. Given the root of a binary tree, which is the node at the highest node in the binary tree, check whether there's a mirror of itself symmetric around its center. So I think we could, high level, maybe define a function which would take left and right nodes, and then compare them to see if they have the same values. In this case, we pass in root dot left and root dot right. Cover function would take left, which would be a tree node or null, and right, which would be a tree node or null, and return a boolean. So in this case, I want to be able to call the function again, where if root dot left, or if left dot val is not equal right, or actually what we could do is return, do this as a sequence of chain logical expressions. We do left dot val equals right dot val, and first we have to check if left and right equal null will return true. But either way, we want to check the values are the same, and then also check, we'll do the helper of, so we're technically at these nodes right now. To check pairwise, we want to do left dot left and right dot right, and helper left dot right and right dot left. We should be able to okay, so that looks good. Ooh. left, I guess additionally, right, if they're the same, you want to return true, but also if left equal null or right equal so if left is equal to null or right is equal, so if one of them is null, now we have to immediately return false, and we do left dot right, and it's null. Oh, for reading val, right? So we right, and for the input, so that looks good. And then the time complexity of this is going to be, we're running helper root.left and root.right. If the two nodes are null, then that means they would be symmetrical, so we return true. And if they're not, if one of them is null, then you want to return false. Otherwise, you want to return the values are the same and they're symmetrical. That would mean that the time complexity time complexity could be, what is the time complexity? One helper dot left and helper dot right. I want to say it's n over 2, which is just linear time, and then the space complexity would be n over 2 as well, so maybe drop the constants as linear time for both trees and the reflections of right subtree. The question is, when are two trees a mirror reflection of each other? Tree is symmetric if the left subtree is a mirror reflection of the right subtree. Two trees a mirror reflection of. For the question is, when are two trees a mirror reflection of each other? Two trees are a mirror reflection of each other if their roots have the same value. Same value in the right subtree. Each tree is a mirror reflection of. It's confusing. I think it's saying if the right subtree is the same as the reflection's left subtree. Tree 1 is the result of n. It's almost the same. Where n is the total number of nodes in the tree, space complexity, number of recursive calls is bound. Recursive calls is bound by the height of the tree. Recursive calls is bound by the height of the tree. In the worst case, the tree is linear and the height is in O of n. Therefore, the space complexity of recursive calls in the stack O of n in the worst case.